All right, welcome to the second lesson of Unit 9. We're going to continue calculating the area between two curves, but we're going to add another method which will make some problems much more efficient and easier. All right, so for our discovery problem, we're going to take a look at the last example from the previous lesson. So go ahead and just sketch out this graph once again and rewrite what we're trying to find here, and then go ahead and press play, and we'll take a look at what we're going to do. Okay, so let's start with this. Think back to the when we did this example at the end of the last lesson, and explain why the two rectangles that I've drawn here confirm why this area in the first quadrant can be computed using two different integrals. So hopefully you recall, of course, that when I use these approximations, the height of each rectangle between 0 and 2 will be found using the square root of x. However, the height of the rectangles from 2 to 4 are going to be found by taking square root of x minus 2, because now I have this red function in the picture. And so when I'm integrating, the heights will be different, and therefore I'll need two different integrals. So you might guess our goal is to find this area using only one integral. Alright, so our goal now is to make an approximation for this area in the first quadrant using rectangles where the height of each rectangle will always be in terms of the two functions. So your goal is to now draw that rectangle. And I'm going to give you a hint here. Try different orientations of the rectangle. Alright, so hopefully you tried rotating the rectangles, and if you do so, when I have this rectangle, I can simply move along the y-axis, and for each point along the y-axis I'll have another rectangle, and these rectangles, when added together, the area of these rectangles will be an approximation for the area that I seek. And so when I take this approximation and look at the limit as the number of rectangles or subintervals approaches infinity, I'll have a definite integral that will give me that exact area that I'm looking for. So we need to figure out exactly how we're going to compute this definite integral. Well, certainly we're going to need to know the dimensions of the height and here the base of my rectangle. How will I find those? And when I do know that, it'll be much easier for me to write out my integral. So let's first think about what makes up the height. Based on where you are along your y-axis, how will you compute the height? So this isn't too hard to think about. I just have to turn my orientation. As I'm moving along the y-axis, at each point along the y-axis, I'll have a rectangle. And this rectangle will have a height that is determined by the x value along my red curve minus the x value along my green curve. So I simply need to be able to ascertain the x value of my red curve and the x value of my green curve at any point y. In other words, I just need to have these functions here written as in terms of x instead of in terms of y. And that way I'll be able to compute the x value at any y value for my green curve and the x value for any y value along my red curve. Luckily, I can solve for x easily in each of these functions. So now I can see at any y value, the x value of my green function is going to be given by y squared. And similarly, for the red function here, the x value for any y at any y value can be found by doing y plus 2. And so now I can compute the height of these rectangles easily. Remember, it's going to be the x value of my red function minus the x value of my green function. So the height will simply be y plus 2 minus y squared. And this should give you a hint as to what this dimension here is going to be. Since I'm moving along the y-axis now, this base here is going to be determined by how many rectangles I have. So when I get to infinitely many rectangles, this change in y, because it'll be a small change in the y-axis, is simply going to be an infinitesimally small change in y, or dy. So now the area of each of these rectangles is going to be the height times this base, dy, And of course, I'm going to be adding all these areas from 0 to 2. And so I need to use the definite integral from 0 to 2 of this height here times the base dy. So go ahead and write it out and try evaluating it on your own, and then we'll take a look at it together. Alright, so let's construct our integral by thinking about the situation logically. We're simply going to be adding up these infinitely many areas, these infinitely small areas, and we're going to be going along our y-axis. Okay, so let's first think about how we construct the areas. The areas are going to be the heights, which we have here, they're a function of y, times dy, which is the base. So our area is this expression here, and we're going to be integrating over what interval? Well, remember, these rectangles are dependent upon where we are along the y-axis. We're integrating with respect to y. Those are the infinitesimally small changes in y. And so we need to go on our y-axis from 0 all the way up to where they intersect, which is at the point 2. So we'll go from 0 to 2. Now, we can integrate this the exact same way we have previously. This is just a function in terms of a variable y. Remember, when we've integrated in the past, this variable here didn't matter. It was just a dummy variable. And so as long as we maintain that same understanding, this function, this definite integral, is just as easy to integrate as every other integral we have seen in the past. In fact, we can integrate this in our calculator using the variable that we have in our calculator in place of y here. So when I integrate, and you can check this, you're going to end up with 3 1/3, or 3.33 repeating, units squared. The exact same answer that we got at the end of the last lesson. However, we did this with only one integral. Okay, so let's go back to our definition here because we've added a new tool to our toolbox. If we are going about finding the area between two curves and we graph both our functions and we're looking at the positions, and it looks a little tricky, so we start drawing the approximating rectangles and labeling the dimensions. And if in doing so the vertical rectangles aren't working, it's just going to look really complicated, and we find that it's easier to create approximating rectangles that are horizontal, then we should do what's called integrate with respect to y. So instead of traveling along the x-axis and creating those rectangles, we're going to travel along the y-axis and create those rectangles. So we're going to integrate with respect to y in place of x. So let's take a look at a graphical representation here. I have two curves, this red curve and the green curve, and let's say I'm trying to find the area bounded by the two curves between A and B here, this region. And we notice in drawing the approximating rectangles vertically that that's going to be really tricky. We're going to have these rectangles are going to be different than the way we compute these rectangles. But if we draw them horizontally, it'll be very clear, right? It's going to be the x value of my green curve minus the x value of my red curve that will give me the height, and I simply need to go between this intersecting point on the y-axis and this intersecting point on the y-axis. I'll draw that rectangle just to make it very clear. And so in order to compute the height, what I'll need is an expression that will give me the x-coordinate of the green curve, so I'll need to solve for x in terms of y for each of these curves, and that will allow me to compute the height. Now I just need to notice which curve has a greater x value. That's going to be the green curve because this x value is further to the right. So it'll be f of y minus g of y. That'll give me my height. And so having solved my equations for x in terms of y, written an expression for the height of my rectangles, I now need to determine the interval of integration. So I need to find what these intersecting points are, and notice that I'm going between the y values of those intersecting points. So we'll call those c and d here. And then I simply need to write and evaluate my integral. This shouldn't be too hard to do. I know that I'm going to be summing up all of these infinitesimally small areas. The areas are the height times the base, so I'll have f of y minus g of y dy. That's the area. And I'm summing up all of these from C to D. And it's important to note, just as we did with our previous definition, that this is representing these infinitesimally small areas, and we're adding them up as we travel along our y-axis. In specifics, this here represents the height of each of these infinitesimally small rectangles, and dy represents the width or the base of those infinitesimally small rectangles. All right, let's go ahead and try a couple of examples. All right, let's take a look at this example here. We want to find the area of the shaded region that is labeled R, and here are the two functions that give these particular curves. Try this one on your own first, and then we'll take a look at it together. All right, so in trying to approximate this area with rectangles, we notice that drawing vertical rectangles is not going to be so easy because we're going to have to write two integrals. We'll have the area underneath the green curve up to 1 and then the area underneath the yellow curve from 1 to 2. Certainly you can do that, but we can do this with one integral if we simply integrate from 0 to 1 along the y-axis, and here all of our approximating rectangles will be the difference between the x-coordinate point of the yellow curve and the x-coordinate point of the green curve. So we need to write an expression for the height here, and that needs to be in terms of y, right? Because we're going to be going along the y-axis. So we need to solve each of these for x in terms of y, as I've done right here. And one thing to note is when I solve for x in terms of y with my green curve, I get the square root of y. And since I'm only looking at positive x values, I only need the square root of y, the positive version. I don't need to look at negative square root of y, which would, of course, be over there. And so now I can write an expression for my height. The yellow curve has a greater x value, so it's going to be 2 minus y minus the square root of y. And now I can set up my integral and integrate. So here is my integral. This is, of course, the height of my rectangles times the base. And determining my limits of integration, I'm going along the y-axis, and so I'm going from 0, and I'm going up to 1, which is where the two curves will intersect. And then I can compute this. And here's my solution. Notice I did this by hand. You should practice taking the antiderivatives when you can by hand and checking with your calculator. Notice that when I evaluate at 1, I get this expression here. Evaluating at 0 gives me 0. So I simply need to combine these like terms and get 5/6 units squared. And you could check if you used two separate integrals to find this area, you'd get the exact same area here, 5/6 units squared. All right, I want you to do one more example. Turn in the book to page 401 and go through example 6. You might need to reread a couple of pieces and think about some of the decisions and some of the words that they use to describe what they're doing, but it'd be well worthwhile. Get this down in your notes and then move on to the homework unit 9.02 on Math Excel.